Hi, and welcome to Dr. V's AP Chemistry webcast. I'm here today to do an overview of chromatography. What I'd like to accomplish in this webcast is I'd like to talk about the experimental setup for very simple chromatography experiments, and we'll talk about the separation method and how this relates to intermolecular forces. And finally, we're going to introduce RF values and talk about how we can use them in the lab. So chromatography is a separation method where you're separating the components of a mixture based on solubility differences. There are a lot of different chromatography methods. So we're going to focus on paper chromatography. This is what I've illustrated here. It's some paper chromatography of inks and dyes. It's a common AP Chem lab to do food dye separations using paper chromatography. I've also done labs with my students where we did thin layer chromatography, which works in a very similar way. A lot of biology classes might do separation of plant pigments using paper chromatography or other methods. But like I said, there are a lot of different chromatography methods using gases, using different kinds of supports, so many different approaches. We're not going to try and go through all of that. We're just trying to get you through enough knowledge of chromatography so that you can tackle what you might see on the AP Chemistry exam. You could take a whole year course on just chromatography methods. So let's talk about a paper chromatography setup, which is the most familiar to most AP Chem students. All right, this is actually an illustration from a lab my students did about a year ago where we had chromatography paper, and that's what we were using as our stationary phase. So we were actually spotting the different dyes and pigments onto pre-cut strips of paper. And then we lowered them into a solvent. And my students were looking at the effects of different solvents, trying to optimize the separation of the dye components. The solvent is referred to as the mobile phase. We were using a liquid solvent. As I mentioned, there can be gas phase chromatography where you might have a gas as your mobile phase. But what we're looking at in paper chromatography is that the paper or the stationary phase and the solvent or the mobile phase have different polarities. And we're taking advantage of that to separate the components. So what you do to set it up is you take your dyes and you actually spot them onto your stationary phase. So here I cut a piece of coffee filter and cut it into a rectangular piece, although it doesn't look that rectangular here, and I spotted them on a line that I had drawn with a pencil because the pencil will not dissolve in the solvent that I'm going to use. All right, and then I lowered it into a beaker. Well, actually, it's my coffee cup. It looks like a beaker, and I lowered the strip into the beaker so that the paper just touches the solvent, but that my dyes are above the solvent. I don't want the dyes to actually go into the bulk solvent. I want them to be on the paper. And then what happens is that the solvent moves up the paper by capillary action, and this causes the dyes to separate. Now, how much separation we get for the dyes depends on a couple of things. A, the nature of the dye, the nature of the stationary phase, the nature of the solvent. All right, so we can manipulate this to try and get optimal separation. Clearly, I'm not getting very good separation of any of the dyes in this particular picture. So if we have good data, you might get something like this for your chromatogram. All right, some of the components might not move very far from the baseline or that original spot at all. Dye A didn't move very far. What that tells us is that whatever is in component A is more attracted to the stationary phase as compared to the mobile phase or the solvent. All right, and that's why it didn't move very far. So if the stationary phase is polar, paper is actually pretty polar, then substance A is the most polar of the four substances that we were separating in this mixture. On the other hand, substance D really traveled pretty extensively relative to the solvent, right? It moved really quite a long distance, which tells us that substance D is more attracted to the mobile phase and has similar intermolecular forces to the mobile phase. So if the mobile phase is fairly nonpolar, then substance D is the most nonpolar component of these four. And we can actually use this to rank them. But this is something you need to be able to discuss on the AP Chemistry exam. I've seen free response and multiple choice questions which address this point. The other thing we can do is quantify how far did a particular substance move, but we need to do it relative to how far the solvent moved. All right, we call this the RF value. So we do need to measure the solvent front, and we measure this always from the original position of the dye. All right, and so we can measure how far substance A moved versus how far the solvent moved. right? So we can measure the salmon colored arrow, and we can measure the turquoise colored arrow, right? And the ratio of these, the distance traveled over the dye, by the dye over the distance traveled by the solvent front, is referred to as the RF value, right? And it's a measure of, again, how, relatively how far did they move. So if we wanted to do this for dye A, we do need a ruler. All right, so the salmon arrow, I can measure to 1/100th of a centimeter. That estimated digit was 1.80 centimeters. The solvent front moved 4.80 centimeters. All right, if I want to do my measurement. And so I can just simplify that, present it as a decimal. You do present it with the correct number of sig figs. And there's my RF value for dye A. Now I could do it for dyes B and C and D as well, but I think once you know how to measure an RF value and how to calculate it, I don't think I need to do all 4 examples. So one of the applications of an RF value is to identify an unknown. So I've got 2 different chromatograms here. The one on the left has 3 known dyes X and Y and Z, and I know what they are. All right, and then I have a second chromatogram for looking at an unknown under the same conditions. All right, and so the question is the unknown the same thing as sample Y? Is that what it contains? Well, this is where you have to be careful, because if I look at how far distance Y traveled, or sample Y traveled, it looks like a pretty similar distance for the unknown from the origin. But they're 2 different chromatograms, and the solvent fronts traveled different distances. And so I can't just use the distance it traveled. I really have to look at RF values, all right, in order to make that determination. So let's do that. All right, of course, we need a ruler. Let's measure how far dot Y traveled from the origin compared to the solvent front. All right, and so I can measure those and measure an RF value. So the sample Y traveled about 2 centimeters. The solvent front was just over 2.5 centimeters. I get an RF value of 0.784. Okay, now we need to do this for the unknown. All right, so for the unknown dye, measuring from the origin to about the middle of the dye front, the sample, all right, was just over 2 centimeters. All right, but the solvent front for the unknown really traveled quite a bit farther. So that was more like 3.60 centimeters. So when I measure the RF value and calculate it for the unknown, I get an RF value of 0.583. 0.770 versus 0.583, they're not the same. And so I'm going to conclude from this that the unknown does not contain sample Y. It's some other component. I can go and try some other things, do some more measurements, but based on RF values, I don't think that they are the same. We have to be careful here. There have been questions, again, from the AP exam where this is the kind of reasoning you needed to do. All right, and so that's what AP chemistry students need to know about chromatography. Thank you for listening, and if you haven't already done so, please subscribe to my YouTube channel.